recording. Page 23. And now we're going to Professor Dave. Let's make it big. Let's make sure our subtitles are on, although maybe we don't need them. I don't know. We'll try. All right, here we go.
It's Professor Dave. Let's learn about the common ion effect.
He knows a lot about the science stuff. Professor Dave explains.
As we continue to learn about solubility and precipitates, we are beginning to understand ways that we can predict or even control precipitation. One such approach we must understand involves something called the common ion effect. So let's learn precisely what this means. The common ion effect is an application of Le Chatelier's principle, which we learned all about in an earlier tutorial.
I don't think this is the one I want. What is happening?
Is it the bottom video?
Well, no, they're the same.
I think it's just the wrong one.
No, I did not click the wrong one. Let's try it again, though.
Professor Dave here. Let's talk solubility.
Oh.
He knows a lot about the science stuff. Professor Dave explains.
Oh my God.
When we first discussed solubility, we learned that some ionic compounds are water-soluble and will completely disperse in solution due to the ion-dipole interaction.
Okay, there's a lot of you who are paying no attention to what's going on up here.
Actions they will make with water molecules. We also learned that other ionic compounds are water insoluble and will not dissolve at all, remaining completely in the solid phase. Beyond this, if the components of such a compound find each other in solution, they will precipitate and leave solution completely to form a solid. This is actually a slight oversimplification that served its purpose at the moment, but now it's time to get a more sophisticated and quantitative understanding of solubility.
Are you with us? Okay.
So let's get a closer look. It's true that many ionic compounds are completely soluble, but the reality is that even the ones that we call insoluble will dissolve to a minuscule degree. Whatever the degree to which dissolution occurs for a particular substance, we can communicate this using the solubility product, abbreviated as KSP. Let's look at a substance like silver chloride, which we label as water insoluble. As we said, if there is an excess of it in water, it will dissolve to a tiny extent and cause a dynamic equilibrium. Some ions dissolve as other ions rejoin the lattice. Just as with any other type of equilibrium, there must be an equilibrium constant to describe it, and that's the solubility product. As we might guess, this will simply be equal to the product of the two ion concentrations in solution, each raised to the power of their stoichiometric coefficients, which in this case is simply 1 and 1. Notice that we do not include the solid itself in this expression, as we do not include solids in equilibrium expressions. The smaller the constant, the fewer the ions that will be present in solution, and therefore the less soluble the substance must be. And compounds that are extremely water insoluble will have KSP values on the order of 10 to the negative 30, negative 50, or even smaller. Let's make sure we can write these solubility products for various equilibria.
Okay, so I think what we're going to do at this point is he's kind of introduced the concept to us. We are going to fill in page 1 with anything we need to. So we have things that are water soluble. So if we put something that is water soluble into water, it dissolves completely. If something is insoluble, which in our book we call low solubility, in our table of solubilities, it will not dissolve in water, remaining completely in the solid phase. Now, that's a bit of a lie, okay? But we'll get to that lie in just a moment. If the components, so that would be like the ions, the components of an insoluble compound. That might be, for example, Ag plus and Cl minus. Say they find each other in solution, they will precipitate and leave the solution completely to form a solid. Now, if we take AgCl solid and we drop it into water, it will not dissolve in the water. That's what it means to be insoluble. But if we were to take Ag plus and Cl minus, now I cannot take Ag plus and Cl minus. There's no such thing as a jar of silver nitrate. How could I get my silver plus ions, my Ag plus ions? AgNO3. So I could take some AgNO3 and I could put it in. I could take some, now how could I get my chloride in there? NaCl. Okay, and I put those in, and what I get then is I get my Ag plus, I get my Cl minus, and those come together and they do what? What do we call that process? Precipitation. They precipitate. So, insoluble compounds, if you take the solid and drop it in, it simply won't dissolve. If you take their components of an insoluble compound, they will come together to form a precipitate. That's a double replacement reaction, yeah. And the sodium and the nitrate would be? Yeah, Na plus and NO3 minus. Are spectator ions. Okay. This model is an oversimplification. Okay? The oversimplification is that no solid is dissolved. But in reality, even insoluble compounds will dissolve to a small degree. So they are mostly undissolved. Solid. But we have a tiny amount of dissolved ions. A tiny amount of dissociated ions. And that is why your book, or your data table, rather than saying insoluble, calls it low solubility. So anything that we call insoluble is actually going to dissolve a very small amount, and that's why we call it low solubility. Okay? Now, just like a Ka, the bigger the Ka, the bigger the degree of ionization. The bigger the Ksp, the bigger the degree of dissociation. So if we consider a low solubility salt like silver chloride, AgCl solid, if we put it in there and we stir it around, a very few ions dissolve. So we have some ions dissolve. However, because we have reached a state of dynamic equilibrium, every time one set of ions dissolves, another set of ions recrystallizes. Okay, rejoin the lattice. The rate of dissolving and recrystallizing. Oh, why am I writing it there? It's right there. Yeah, look at that. That's exactly what I wanted to write. The rate of dissolving is equal to the rate of recrystallization. So the forward rate is equal to the reverse rate, and therefore we are at a dynamic equilibrium. And what's happening to the concentration of the ions? The concentration of the ions. What's happening to it?
Depends what the stress is.
No, I've just dissolved some, I've stirred it, and now it's just sitting there in a dynamic equilibrium. Yeah, the concentration of the ions remains constant. And remember, what kind of a property is concentration? It is a macroscopic property. Concentration is a macroscopic property. And when we are at equilibrium, all macroscopic properties remain constant. Okay. So this here, this first beaker, this is dissolving. And you can see two particles come up, right? We got those two little arrows coming up, a green and a red. And then we have recrystallization. And you can see a green and a red come back together and join onto the lattice. So overall, the concentration is remaining the same. So really, we're starting here with these are our original concentration, yes? Two particles come out, but two particles go back in, so we end up with 4 particles just like we had at the start. Now we have our KSP. This is the math part, which is always kind of nice because it's kind of a little bit straightforward. So we always put the solid on the left. In a solubility equilibrium, equation, in a solubility equilibrium equation, which I'm often going to refer to that as the S.E.E. solubility equilibrium equation, the solid always goes on the left. Solubility equilibrium equation. And there's a reason for that. It just makes the math tidier. If you had the ions on the reactant side, it would always have to be 1 over your ion concentrations. Whereas here, your products, the ions, just go nicely on the top and we don't have to write 1 over those. Does that make sense? Yeah? Okay. Anyway, so we always put the solid on the left. It makes our math more simple, and it means that we can all use a table of KSP values, which you will find on page 5 of your data booklet. So grab your data booklet, take a look at page 5. All these values are based on the fact that the solid is on the left. What would we have to do with those values if we put the solid on the right? We would have to do the reciprocal 1 divided by that. Okay, and that just sounds like more work than is necessary. So all of these have the solid on the left, so we don't have to do any 1 over nonsense. Okay. So our KSP expression, then we take our products, Ag plus times Cl minus. Do you need to include the charges? Yes. Okay, so there's our charges, plus and minus, and KSP equals, this is our KSP expression. Whoops. Okay, and just like your Ka expression, anytime you use a KSP, you need to write the KSP expression. So anytime you use a KSP in your work, you should be writing the KSP expression, just like KAs. Anytime you used a KA, you would write the KA expression. KSP is just the special name for the KEQ, for solubility equilibria. We raise them to the powers. Here we have no coefficients, so it's just raised to the power of 1. And just like all other equilibria expressions, we do not include solids. So there we go. Oh, and here we see easy math, hard math. Well, not hard math, but harder math. And this next bit is not in the Professor Dave video at all. We are going to talk about the solubility equilibrium equation, which we've just been introduced to today. What do we call the solubility equilibrium equation if we want to abbreviate it? That's called the S.E.E, the C. Now, precipitation equation. Can you guess what a precipitation equation is? That's your precipitate, that's the PPT. That's what you were doing when you wrote the complete ionic and net ionic equations back in section 3.1. And we're going to call that the PE, the precipitation equation. Formula, equation, the complete ionic equation, and the net ionic equation. When we did the solubility equilibrium equation, where did the solid go? It went on the left. Excuse me. So, solubility equilibrium equation, the C. Solid is on the left. And it is an equilibrium. So what kind of arrow do we use? The double arrow. We use an equilibrium arrow. When we were writing the precipitation equations, when you write your equations on your quiz on Thursday, where did you put the solids? Was the precipitate the reactant or was the precipitate the product? The precipitate is the product. Okay, in a precipitation reaction, we are forming a precipitate. That means the precipitate is the product. So where does the solid go? In a precipitation equation. It goes on the right. And what kind of arrow have you been using? One-way arrow. And that's because we don't care when we're doing a precipitation, we don't care about it dissociating after it precipitates. And if we do, then we would do the precipitation first, and then we would show it going into equilibrium. So we would show first the precipitation equation and then the solubility equilibrium. Okay? So here we have, we're going to look at situations where precipitation occurs. And then we will also look at, oh, sorry, that's what I'm talking about. When later on, we'll look at a situation where precipitation occurs, step 1. So we would show it like this, where we have our ions going to the solid. That's our precipitate. So precipitation occurs, then next an equilibrium is established. So our solid then goes on the left, and we have our ions on the right. First, we would have our precipitation equation. Second, we would have our solubility equilibrium equation. That's going to be more complex. We're going to be looking at that later. Okay? Most of the time, you're going to be using one or the other. Be sure you are always writing the equation in the correct direction and using the correct arrow. You will lose marks if you choose the wrong one. Okay? Now, what we're going to do is we're going to take a look at questions and see, these are questions that we'll actually do the math for later, but we're going to see if you can tell whether this will be a precipitation equation or whether it will be a solubility equilibrium equation, and then what you would use, and then which one you would use, and then you're going to write the actual equation itself. So read that first one. Write the net ionic equation that occurs when we mix BaCl2 is mixed with NH4 2SO4. Is that going to be a solubility equilibrium equation where you're working with KSP, or are you just trying to write the precipitation reaction? This is the precipitation reaction, the PE. Okay, precipitation. So could you please write the net ionic equation that occurs? Ooh, that's tricky. You might want to write the formula equation first. So I'm going to write that up here. Is Ramina's here, right? Okay, yeah, I'll give this to her. Yeah, thank you. So this is practice for your quiz on tomorrow, Thursday. Ooh, boy.
That means there's no reaction. what did I show for the shortcut method?
Yeah, I'll go through the shortcut method. Yeah. Okay, so we have these ions. So barium 2+ is going to get together with sulfate. So we get barium sulfate. Is that a solid or is that aqueous? That is a solid. And then the NH4 is going to get together with the Cl. Is that solid or aqueous? Aqueous. Now, let's do the shortcut method of writing the net ionic equation. All we do is we take our solid, BaSO4, we write it on the right, we put an arrow going towards it, and then we say, what do we need to make BaSO4? Ba and SO4. Make sure you put in your states, aqueous, aqueous. And there we go. Yeah? Okay. All right, so that's a case where we have a precipitation reaction. We have our one-way arrow. The solid is on the right. We don't care about, we're not doing anything with KSP, so we do not need the solubility equilibrium equation. The next one says the molar solubility of PbI2 is 1.52 times 10 to the minus 3 molar. What molar solubility is, that is the maximum concentration. Solubility is how much will dissolve. And it says to calculate the value of KSP for PbI2. So which equation will we be using? Will we be using the PE or the CE? The C, the solubility equilibrium equation. Do you guys want to see how easy these questions are? We're not actually doing the math part of it at this, like in section 3.2, but let's just do the math anyway, because it's really easy. Okay, so we're going to set up a rice table. Okay. Technically, it really doesn't need a rice table. Do you want to do it without a rice table? Yes. Okay. Our concentrations. What is the concentration of lead iodide? 1.52 times 10 to the minus 3. That means that's how much dissolves. So how much? Ooh, did I do that right? No, I didn't. What did I do wrong here? I missed so many things. I got so excited that I missed, what did I miss in my solubility, in my S.E.E.? I missed my states, solid, aqueous, aqueous. What else did I miss? I missed the 2 before the I. So if lead iodide is 1.52 times 10 to the negative 3 molar, What is the concentration of lead? It's the same. 1.52 times 10 to the negative 3 molar. And what is the concentration of I? 2 times 1.52 times 10 to the negative 3 molar. So easy, yes? Now we know the concentrations of the PB and the I2 and the I. How would we find the value of the KSP? First, we would need to write the KSP expression. Can we do that? KSP is equal to, what does it equal? Concentration of PB2 plus times the concentration of I minus to the power of 2. And then that's going to be equal to, and then we just plug in our numbers, 1.52 times 10 to the negative 3 times, oh my God, I'm running out of room here, times, and I'm going to multiply that by 2 because I don't want to have to write it out. It's too much room. 1.52 times 2 is 3.04. 3.04.
And we just make it to power of 3 though. All three of them are the same.
They're not the same though, because this is 2 times. Yes. So we multiply it by 2. Okay, so we have that 2 times. So that's the 3.04 times 10 to the minus 3. We have our 1.52 times 10 to the minus 3. We need to square our iodide, so we're squaring the iodide. And then we get 3.04 E 3 negative squared times 1.52 E 3 negative equals 1.40 times 10 to the negative 8. And even though you haven't learned how to do that math yet, is that difficult or is it easy? Pretty easy, easier than KA stuff, right? Don't have to do the whole rice table. You can just do your concentrations right underneath. Just make sure you get the coefficients in there, okay? All right, this one's tricky. A student titrates. Ooh, do you guys remember what a titration is? When you have a titration, you take come on, move over. There we go. When you have a titration, you have this big long tube. What do we call that big long tube? That is a starts with a B. Burette. Yes. Okay, that's a burette. And down below the burette, we put one of these flasks. What's that called? That's an Erlenmeyer flask. Okay. And we want to titrate, we're titrating 100 milliliters of well water. And we are told that there is chloride ion in the well water. Yes? Well water, chloride ion in the well water. You have to be okay with the fact that there's information about the well water in the first sentence and in the second sentence. You need to be able to read and comprehend.
Well, hi. Sorry, I don't want to interrupt. So,
Interrupt away.
oh, interrupt away. All right.
Interrupt away.
Free reign. All right. Hi. We have a winner for last week's candy in a jar. Yeah, you're the winner. You know this. Okay, that is the winner.
Oh.
So, yeah, you can applaud for him. Yes, he wins everything in the jar.
Nice.
But he doesn't win the jar, so there's a ceremonial dumping of candies in a bag. There you go. Yeah.
Oh, okay, you should applaud that as well.
You don't applaud it. All right, there you go.
What did he do?
There's candies and a gift card, so congratulations. I don't know that one, because that one has no actual money in it.
You don't want the one with the money.
Yeah, you don't want $2. I don't need this bag back.
And you get a bag.
And you get a bag.
Whoa.
There you go. Thank you. All right. Congratulations. All right. Hey, winner.
Okay, so we're just going to finish up with the next 5 minutes because it's till 12:25. Okay. None of this, you won't have any homework related to this because your homework is going to be studying for your quiz tomorrow. Okay. On section 3.1. So we got our Erlenmeyer flask, and in our Erlenmeyer flask, we have some well water. And it contains chloride ion, Cl-. There's also positive ions in there, probably some sodium, probably some calcium, who knows what. Okay, but the chloride ion is floating around because it doesn't precipitate with anything except for silver, lead, and copper 1. Okay? So the chloride is floating around in there, and we've got some positive spectator ions, but we don't care what they are. Up in our burette, we have some 0.1 molar AgNO3. Okay? And we want to precipitate the chloride ion. Are we going to use the precipitation equation or the solubility equilibrium equation? Are we going to be forming the precipitate, or are we looking at what happens after the precipitate is formed? Yes. We're looking to precipitate. Okay? So this is going to be a precipitation equation. PE. Now this can confuse students a little bit because they're like, I have chloride, I have AgNO3, and I have chloride. Oh, that's ugly because one of them has a partner and one of them doesn't. What could I do with the NO3? I could just get rid of it because it is a spectator. Get rid of it. Okay, because it's just confusing when you have one with a partner and you have one without a partner. So try to get rid of the partner that you don't need. You could write it this way. You could say, okay, I end up with AgCl solid plus NO3 minus, but a lot of people find that confusing. Okay, and I don't blame you. It looks weird. Okay, you could do that. But if we get rid of it, it becomes Ag plus aqueous plus Cl minus aqueous goes to AgCl solid. And our solid is on the right. And we have a one-way arrow. That's our precipitation equation. So this one here is harder. The one on the top is harder. The one on the bottom is easier. Study hard for your test tomorrow, not test, quiz. And I will see you then.